right. So you can watch the first video I uploaded on the YouTube site that I have. And the link is on the LMS. And the first part of our first lecture contains the important material about the course syllabus and about the grading scheme and the project 1 and 2. So please read through carefully and don't confuse what we're going to do on this semester. But yeah, before we start, is any other questions about any questions about the class? Or no? Okay, so let's start. So so before I start, let me say that we're not going to make a group until we have final roster. So I think we're gonna make the group on the 3rd week. So from then you can work on your project. All right, so here we were. So we were at the very end of the sequence part. So let's see. So I want to go slow, but also if you want to go deeper, there are so many stuff going on because calculus is basically a mixture of analysis and geometry. So if you want to go deeper into the specific part of our calculus business, then you have to go to the mathematical major. So here, let me briefly define what the sequence was. And I'm not going to repeat the same thing. Sometimes I will just rephrase in different wording. So I'm going to do it right now. A sequence AN. So we talked about this as a list of number, but we can also define a sequence as a function from the set of natural number to the set of real number. So usually we take the natural number that contains 0. 0 is a natural number, but it's a tradition that our index of a sequence start from 1. So I changed the domain set as a set of natural numbers starting from 1. So it's a function basically, but it's not just a function. The reason why we study sequence is to find out what's the behavior of a sequence as I increase the index. So a sequence AN is said to be convergent or said to be converging to L if, so I'm going to, again, rephrase it in a different wording, but I want you to not take one of these definitions, but you take all of the definition and think about why one definition is matching in a core meaning to another definition. So we say the sequence AN is said to be converging to L if this decreases to 0 as n increases. It's a kind of a vague meaning, but you can, if you look at the epsilon delta definition we talked about at the end of the class, you can see the why this makes sense. So let's say, and also a sequence is AN is called divergent if it's not convergent. All right, so let's look at the example here. So I have AN, let's say I define AN as value 1 or 1 over n. So 1 if n is even, it's an even number, or 2, 4, 6. And when it's odd, let's define it as 1 over n. Now, Is AN convergent or divergent? Just guess. Do you think it's convergent? So does it matches to our definition, the meaning of the convergent? So you have, do you have L? What is L if it's convergent? No, so for AN. So AN is defined to be either 1 or 1 over n, depending on the index. So if you want to say it's convergent, you need to know what the L is, called the limit, and then it matches to our condition here. It's not convergent, right? Yeah. So let's check with the graph here. So let's draw the graph of a sequence. It's not really good for my eye. Oh, okay. So secret. Mm-hmm. But sorry, yeah, I have a question. Yes. Yes. You mean, are you asking whether you can have a presentation by recording? So sorry, what's your question? What's figures or videos?
I'm asking about like lecture notes.
Yes.
We have like presentations, or we have only video recordings of our lectures.
Oh yeah, I don't have. I have a lecture notes, but it's a handwritten, so I don't know how to share this.
Okay.
Yes.
That's only video recordings.
Yes. All right, so let's define our. Oh, sorry, to make it bigger here. Everyone can see from the back. Can you see it? Okay. So we have n goes to float. So it depends on whether it's even or odd. So when it's even, that means if you divide the n with 2, oh, by the way, so again, so if n is less than or equal to 0, then I want to return not a number. And if it's even, is it 1? Yes, the return 1. Else what? If it's not even, then return 1 over n. All right, so let's just put it together. So I'm going to import pyplot as plt, and let's draw a graph. So we have I for I in the range of 1 to 11. I'm going to draw 10 points, and y as a of I for I in x. I'm going to draw x and y. Okay. So what do you see? Okay, so it's kind of oscillating. So actually, it's connecting all the points that I put in X list and Y list. But the sequence is actually a discrete object, so it's not really a smooth curve. It shouldn't be a smooth curve. So instead of connecting all the points, let's just put the dots here. So so I can make a dot figure. It's just too big, so let me just show it a little bit smaller. So you can see that as I increase my index, so x-axis is the index here, the value, which is the y-axis, is jumping from 1 to 1 over n here and here. So we know that it's not convergent. So this is not something that we can call from convergent. Although in some part of sequence stabilize at 1, some part of the sequence stabilize at 0, we don't call this convergent. Because why? We cannot find a single L, right? So, but how do we prove it? So proving not convergent or divergent is a different story. How do you prove it? Yeah, so basically, so I think you're talking about the proof by contradiction. So if you assume that there is such L, then we need to find that it's not satisfying the rest of the story here. So let's say if L is 0, let me start by saying that assume, so let's say, let's proof of AN being divergent. So let's assume that AN is convergent. And then a contradiction is there. Okay, so there are many ways. There's no fixed way of finding a contradiction, but let's start from, let's say, what I have to do is there's no real number, not any single real number can be L satisfying this situation. So I want to split the case when L is 0 or L is not 0. Okay, okay, so if L is 0, let's see why it doesn't make sense. So if L0, the 0 is the limit of a sequence, then AN minus 0, which means just AN, has to decrease to 0 no matter how I increase my n. But here, there's always a sequence value which is 1, no matter how my n is big. So this doesn't make sense. And how about this one? If L is not 0, so it must be somewhere in above 0 or below 0. If it's below 0, then there's no way you can get close to minus value. And if it's above 1, then there's also no way you can close to that value. And if it's between here, it's also clear that there's no sequence that it's going to close to any value in between 0 and 1. So basically, that's the way you can prove it. The writing down the proof is different skill. You don't need it if you don't want to be a math major. But the same idea has to be there, even if you're not a math major, because this is the logical way of thinking whenever you think about the statement. So either case, there is a contradiction. I mean, there's nothing, satisfying this. What's contradictory here? Because we assume that this L is a limit. It's contradictory to our definition, so that's a contradiction, right? So for some, it might be very obvious to you by looking at the graph, but sometimes when it gets really complicated, then you need some logical idea of how to, at least to get the conclusion, because sometimes you don't see the nature of the sequence by just looking at this graph. So let's introduce one more property here, and then move on to the sequence part, series part. So whenever you have two sequence, so I'm going to write down the limit of a sequence as this symbol. So this is just a symbol that indicates that an has a limit, and this whole thing is representing that limit. So let's say bn has a limit m. Then first of all, if you take a new sequence whose nth entry is the sum of nth entry on the sequence A and B, then the limit exists, which means the sequence also is convergent, and the limit is L plus M. And same thing for the multiplication. If you make a new sequence, so this is not the old sequence from A to B. You made a new sequence whose nth entry is the A times B, and then it says the proposition says that it is convergent, and the limit is L times M. So it's not a formula, it's a statement. It's a statement that there needs to be proved, but we don't prove it right now, just because it's already proved in analysis. So you just accept it, and then you can apply it to the situation you want to solve. And another one is if you divide out two sequence elements, and if m is not 0, then the same thing holds. So we have kind of L over M as if the limit is distributed here. And the last one is if you have another sequence, Cn, which lies always in between A and B, and if the limit of A and B are the same, meaning that the L and M are the same, then this sequence, which lies in between A and B, also convergent, Cn, and then the limit is L. So it's called the sandwich theorem. So there are many form of sandwich theorem, but this is one of the forms. So let's think about the examples here, how to apply these propositions. So I'm going to just give you another insight of the limit of a sequence. Could be different from what you learned in the high school. So let's think about this. So everyone knows this. What is it? 1. Why is it 1? So some people think that, oh, n goes to infinity, and n plus 1 also goes to infinity, and it goes with the same speed. So it's an infinity over infinity with the 1s on the coefficient on both sides. So it's 1. It's kind of true if you look at the graph, but infinity is not a number. So logically, it's not make sense. If you consider infinity as if it's a number, then you can fall into lots of traps. So the correct way of doing this is, okay, so I want to think about n over n plus 1 as if it's 1 over n divided by 1 over n plus 1. If you divide it into, divide the numerator and denominator by n, this is the sequence. This is the another form. So then let's call this an, and let's call this bn. What's the limit of an? 0. And what's the limit of bn? 1, right? And here, let's apply the property 3. So m is not 0 because it's 1. Therefore, it's 0 over 1. Sorry. A mistake? Sorry, not over 1 over n. So what am I doing here? So I divide by n, just 1, sorry. So 1 plus 1 over n. Sorry. Okay, so what's the an here? It's a 1. Yes, so the limit is 1. And what's the limit of bn? It's 1. Okay, so m is 1 and L is 1. So it's L over m, which is 1 over 1. So it's 1. So this is how you can apply the proposition here properly. Okay. So let's see another one. So what if I have n over n squared plus 1? What's the answer? Just the answer. What's the answer? You knew this, right? What's the answer? 0. Why is it 0? Why is it 0? Everyone knows it's 0. Yes, why? Why that makes it 0? Yes, in the divider, n squared plus 1. Yeah, n squared plus 1 grows faster than n. Has to be much bigger than the numerator. So it's almost like 1 over infinity. So it's 0. That's how we think. But there are lots of gaps in the logic, right? So there are lots of traps they can fall into if you do the computation like that. So let's try to use the proposition. So how do you use the proposition here? Same way we did here. First, you divide by n, and then, or maybe what happens then? So n plus 1 over n, yeah, when you divide by n. So now, can you use any of the property here? Okay, so I can probably set this as an, and also this as bn, but does it satisfy our assumption here? The limit of an is 1, but the limit of bn is what? It doesn't exist. Yeah, so we call it limit is infinity to say that it's divergent, but in principle, the logical way of saying is that there's no limit. So we cannot, I mean, this proposition is with assumption only when the an, bn converges to a certain number, but bn has no limit. So you cannot use any of the property yet. Let's divide n by n again. So it's 1 over n, 1 plus 1 over n squared. Now what? So this is our new an, and this is my new bn. What's the limit of an? 0. And what's the limit of bn? 1. Yeah. So you have to prove y is 1 over n squared equals to 0. The limit is 0, but I think it's easier, relatively easy. So it's 0 over 1, because now you can apply this property again. So it's 0. Okay. How about this one? Sorry, question? So how about this one? The limit of 1 over n sine 1 over n. So what's the answer? Just an answer. Anyone can guess what the answer is? No? Well, if you don't know the answer, that's why you need to use the computer, right? You have to guess. You have to at least know whether the sequence convergent or not. So let's draw again. So I can just change a little bit here. Everything is almost similar. I just copy paste, and I change the definition of A. So I will just introduce another way of defining a function called the lambda function. Let me make it bigger. So lambda function let us to just write down the formula and define a function in a one single line. So here I have 1 over n times, yeah, I have to use the sign, so let's import another important package here, which called the numpy package. Oh, sorry, I don't think I need, sorry, so n, and 1 over np sine 1 over n. So this is a lambda function, and let's you define it quickly about the formula, and then define it here. So 10 points are still small. I want to draw 100 points. So let's see what happens here. So You can see it's very oscillating, kind of oscillating. I think you have to put the line, dash the line here to really show what happens. So it's kind of decreasing very fast, but that's because I have plotted from 1 to 100. So let's take a small portion of this graph. So instead of putting 1 to 100, let's say 20 to 30. That's still decreasing. Am I did right? The MP sign, yeah. So how about 25? Yeah, it's not really showing how it's really oscillating here. MP sine 1 over n. Yeah, well, it doesn't really show you the oscillating part, but it's not really straight or 1 over n curve. So if you compare the curve with a graph of 1 over n, which goes smoothly with a hyperbolic curve, to this graph of a sequence, it's not really smooth, but it's kind of a wiggling here. But anyway, you know that it's decreasing to 0. So, and also we can guess that this is convergent and convergent to 0. So let's try to prove y has to be 0. So which property do we have to use here? So I'll give you a hint. It's either 3 or 4. Which property do you think it's appropriate? Is it 3 or 4? 4? Yeah, it's 4. Although you can think this as a kind of sine something over n, right? But then you cannot set the numerator and denominator as a n, b n, because a n we don't know the convergent. Actually, it doesn't converge, and b n also diverges. So let's use number 4. So this is my new sequence Cn. So let's say I have an equals to minus 1 over n, and bn as plus 1 over n. And what? My Cn is right in between these, right? And what happens to an? What's the limit of an? 0, right? And here it goes to 0. And this also has to go 0 by the sandwich theorem, right? Therefore, it has to be limit to 0. So you can change this too. You can have n here. So if I change this to n, then I think you can go see more wiggling happens here. So instead of 1 over n, let's take n here. So let's draw 1 to 25. So you can see the wiggling here, but it's still convergent to 0. So in this case, your sine is taken at a range of 1 to infinity. So sine is oscillating from negative value to positive value. But in the previous example, we had 1 over n, which is always positive. So sine positive is always positive when the value is small. So we don't see the wiggling, but you can see the wiggling here. But still, if you compare this graph with a 1 over n, let me draw one more graph here. So y is going to be 1 over I for I in x, and plot x and y. So I'm going to not make a dash. And let me do another one. So instead of this y, let me put minus 1 over n. Let me put the dash here. Oh. PLT plot. Okay. You see, so the above dashed line is the kind of a graph of a sequence AN, which is above the sequence CN, the example here. And then the green one is the sequence Bn, which is below the sequence here. So you can see that A and Bn converge to the same number, 0. Therefore, the in-between, whatever, however it oscillates, it has to be convergent to 0. Right? Any questions? No? All right, so let's talk about the series. There's, okay. Okay, so what is a series? Let me define it first. A series is the sum of a sequence, not just any sequence. If you want to make a meaning out of the sequence, a series, then you have to add infinite sequence. Now, the series are a little bit tricky to understand if you really think about this. Usually, we write the series as something like this. You have a sequence AN, you sum them up from when index n goes from 1 to infinity. So it's like AN plus A2 plus forever. So what is it? So how do you define even something that is going infinity? Like, you cannot add anything infinitely many times. So how do you even define this? So this is actually, it's a definition, but it's actually the limit of another sequence called the partial sum when n goes to infinity. So here, partial sum, S is for sum, is the sum of first n entries of the sequence AN. So this is the partial of the series, the infinite series here. And if the partial sum goes to infinity as you increase the latest index here, if it converges, then we say it's a series. Of course, the series could diverge. So that means that if I take the limit of partial sum, the limit doesn't exist. Still, in that case, we write the same notation here. So this notation doesn't mean that always the whatever you've written down with the certain sequence converge, but it could diverge too. We have to check whether the series converge or diverge. And if it's converged, what's the limit? So the simplest sequence or series that you can think of is a geometric series. So here we have 1 over 2n, n equals to 1 to infinity, which is 1 over 2, 1 over 4, 1 over 8, and it goes forever. We know that it's convergent. I mean, without even thinking about mathematical analytically, you can think about the one by one square box. So if you take the half, it's 1 over 2. If you take the another half of the rest of the half, then it's 1 over 4. Another half, it's 1 over 8, and it goes forever. You're going to fill out all the missing areas in the square, and it's not going to exceed the area of a square. So you know that this is equals to 1. It's always equals to 1. But you can also prove this mathematically by definition. What's the partial sum? So it's 1 over 2k. So if you take a finite sum, there is a formula for that. So we have 1 over 2 to the n. Sorry, let's start from 1 over 2. What's the formula of this geometric series? You take the first entry, 1 over 2, and then, is it 1 over 2? Yeah, it says It's 1 minus 1 over 2, which is the common ratio, and then what? 1 minus 1 over the number of elements in here, which is n, times the first entry here, right? Is it right? Yes. So you have a 1 minus common ratio, 1 minus the common ratio to the power of the number of some n's, and then multiply with the first entry here, right? That's the fine. I mean, this is quite obvious from high school, right? Even if you don't remember, you kind of remember your experience that you have seen this kind of formula, right? If you don't know this formula, then you probably shouldn't pass any exams that enables you to enter in this school. So anyway, that's the partial sum. So what's the limit of this partial sum? You want to take the limit of this formula. It's already a sequence, another type of sequence, 1 over 2 to the n, 1 minus 1 over 2. And we use the same proposition about the sequence. When you take the limit, you can take the ratio of, and then what is it? So in the denominator, you can put 1 over 2 either direction. When you put the on top, let's say, it's 1 over 2. The limit is 1 over 2, and the limit of the denominator is a constant sequence, so it's always 1 over 2. It's 1, right? So we know that this series is 1. Let's do another exercise. Let's do another exercise here. How about 1 over n squared? Is it convergent or divergent? So you want to add first 1 and 1 over 2 squared, which is 4, 1 over 9, 1 over 16, and goes forever. So what is mathematics about? It's about projection. So you have to make a projection first. We have to have an idea whether it's convergent or divergent. Where does this idea come from? It's come from the experience. How do you get the experience? We have a computer, or you can do a hand calculation, but computer is much faster and reliable. So let's try to graph the graph of a partial sum. So when I say, well, I want to graph the series, I'm not trying to graph the point and graph the value of the limit. I want to graph the partial sum sequence. So let's define a partial sum of that series. So I'm going to, let's say, define a variable called sum. Let me make it bigger. And this is going to store my entire value of the partial sum. So when n is the index of my partial sum, so what I'm doing here is for I in the range of n, so I'm doing it n times, and sum plus 1 over I plus 1 squared. So why do I take I plus 1 instead of I? Because when I take the range n, this range, this is the original function that Python defines without any important import. Always start from 0. So when I do this, I start from 0. I don't want 1 over 0. I want 1 over 1 for the first entry. So that's why I add 1. And it goes n times. So I don't need to worry about whether I achieve n. It will achieve n. And then return this sum. So if you want to be really precise, you have to handle the exception when n is less than or equal to 0, but let's not do it. So let's draw the graph by doing this same code. And where did I missed here? Defines S. Did I use S somewhere else? Oh, here. I made a mistake. Oh, okay. So, sorry. So I made a mistake. This is not the proper way of doing squared. This is the square. Yes. All right. So yeah, no problem here. And you can see that the graph is increasing, of course, but it's the slope is decreasing, and it's kind of leveling off. But I don't know because I just draw the first 10 partial sums, so it's not enough to conclude that whether it's bounded above or not. It could go infinite. So let's draw 100 points. Okay, so if I draw the 100 points, yeah, that looks kind of flat, but still not convinced because log function almost looked like similar. You know, it could go very slowly up to infinity. So let's do it in this way. So instead of increasing my x-axis by 1, let's increase by 10's power. Okay, so instead of just having I, I'm going to have 10 to the power of I. And then my I is not the index, it's the exponent of index. So I cannot make it into 100 because it's going to be 10 to the power of 100. So let's say I have 6. Yeah, so then I'm going to increase, let's say I can just take it into just 6. Okay, so then what I'm doing here is increasing my x coordinate from 10 to the power of 0, because I now start from 0 and up to 5. So I'm going to draw 6 points from 1, 10, 10 to the power of 2, 10 to the power of 3, up to 10 to the power of 5. And then draw the graph of this partial sum. When I do this, x-axis is going to be not properly scaled because, you know, 10 to the 5 is very far away from the 10 to the 4th, and the rest of the points are going to almost invisible here. So I'm going to change my x scale as log scale. So this is how it looked like. So you can see that the bottom here is not equally spaced. So you see there's a distribution of the ticks here, meaning that it's the so the length doesn't properly indicate the actual length between two numbers. So this is increased by 10th power, but still I can see all the numbers in a nice way. So it's a log scale. And you can see that even if I increase my index up to 10 to the 5, it still kind of, doesn't increase that much. So it gives a nice intuition that it must converge. It shouldn't go infinity. So how do we prove it? How do we prove this is convergent? So now I have an kind of a projection that it has to converge. So the proof of convergence of this series. So remember that theorem we talked about last time. The theorem is about monotonic increasing but bounded above sequence. So if a sequence is first monotonic increasing and second bounded above, then what? AN, the sequence AN, converges. So we're going to apply this theorem to the sequence of partial sum of this series. So let's write the partial sum sequence again. So Sn is sum of 1 to n of ak. So here ak is 1 over n squared. So here an is 1 over n squared. So don't confuse with an in the theorem. So this an is just any sequence. So, and this is 1 plus 1 over 4 up to 1 over n squared. And the first property, monotonic increasing, is it true? So Sn is, so Sn plus 1 is Sn plus 1 over n plus 1 squared. It's just adding positive number. Positive at the next addition of positive number gets smaller and smaller, but still it's getting increasing, right? So it's definitely bigger than Sn. So it's monotonic increasing. How about boundedness? Is it bounded above? So how do we prove it? So what I need is, for any n, I need some value which is always greater than m, no matter what my index n is. So let's rewrite my partial sum here. 1 plus 1 over 2 squared up to 1 over n squared. And so it's a trick. So I'm not saying that everything can be solved this way, but you need a clever trick. And this is simply 1 over 2 times 2, 1 over 3 times 3, and up to 1 over n times n. And this is actually smaller than 1 plus. So I take one of the factor on the denominator of each summand and then lower it by 1. So instead of 2 times 2, I get 2 times 1. And then instead of 3 times 3, let's make it 3 times 2. So when you get the smaller denominator, what happens to the ratio? The ratio gets bigger, right? So it gets bigger, strictly bigger, all the way up to n times n minus 1. Now, what can you say about, let's erase this. What can you say about these parts? Let's continue on the left. So this part is simply 1 plus. So here, 1 over 2 times 1 is 1 over 1 minus 1 over 2. Right? It's 1 over 2, of course. And how about 1 over 3 times 2? It's 1 over 2 minus 1 over 3. You see the pattern here? What's going to be the next? The next one is 4 times 3. It's 1 over 3 minus 1 over 4. So if you try to make a common denominator by multiplying the denominators on each side to ratio, then it's going to be always the numerator is going to be the difference between two denominators here. So it's going to be always 1. So you get this 1 over n times n minus 1. So then what? You can cancel out everything in the middle all the way up to here. 1 minus n minus 1 over n minus 1. So what you're left with is 2 minus 1 over n. So every partial, so again, so let's make it clean. So we started from Sn. We concluded Sn is always strictly less than 2 minus 1 over n. And can you find any constant number which is strictly bigger than 2 minus 1 over n? 2, yes. So this is my m. So Sn is bounded above. So what did we say about the theorem? The series of partial sum converges. Therefore, this converges. So before you prove anything about the convergence and divergence of a sequence or series, you need to have an idea what to prove. So we decided to prove its convergence, and we used the theorem that is available. And okay, so before we move on to the next one, is there any questions? No? Okay. So we have tests in the series. We have lots of tests we can apply to in order to find its convergence and divergence. And I think some class in the engineering mathematics covered this stuff, and I'm sure that the single variable calculus covers this, but I think some people have not heard about this. I will cover the convergence test here. So convergence test. So the full list of tests are in the book, so I advise you to read the book. I'm going to list a few important things here. So the nth term test. So it says that if you have a series where its sequence does not converge to 0, it always must diverge. So if an not goes to 0, I mean, even if it converges to some number, if that limit is not 0, then the series of that sequence always diverges. Diverges means it's not convergent. So that's the nth term test. So let's look at the example. So if you think about the sequence, a series of this form, does it converge or diverge? Diverge or converge? Say it again. Diverge. Why? Yes. So if you take this as an, where does it go? Not really 1, but not 0, definitely, right? We know that it's not going to be 0 because we have 1 plus something to the power. It's nowhere we can get to 0. So it doesn't actually goes to 0. It goes to some number. It's called the natural constant anyway. So that's divergent. And that's another test. So this is the test you have to think before you apply any test for the convergence and divergence of series, because this rules out most of the series when you check the convergence. So alternating test. Alternating series test. What this is about. So if you have an alternating series, which means that the sign of the sequence element is oscillating from 1 to -1, like it's not randomly oscillating. It's always plus and minus in this way. So an is always positive number here. So it converges if an goes to 0. So the reason why I'm mentioning this is you shouldn't confuse with the nth term test. So alternating series test says it's enough to see the convergence of your sequence, the absolute value of your sequence, whether it goes to 0 or not, to conclude that the alternating series test, conclude that the series is convergent. So what happens when the limit is not 0? By the nth term test, your series is not convergent, divergent. So it only works for the alternating series test whenever it has alternating sign. If it's not alternating, has no alternating sign, you don't know whether the series converge or not, even if the limit of the sequence converges to 0. There are sequences that goes to 0, so here is an example. So let's see these two series. -1 n, 1 over n, when n is from 1 to infinity, and another one, which is just 1 over n. So is this series converge? Yes, because the absolute value, 1 over n, goes to 0. By the alternating series test, this converges. How about this one? The series of 1 over n. Is this convergent or divergent? Yes, it is divergent. Why? We need another test, but at least here we cannot conclude that it's convergence just because that 1 over n goes to 0, because it's not alternating series. So the answer is divergent, but we need another test to conclude this conclusion. So anyway, I just wanted to make that clear. So nth term test only checks whether it's divergent, and it does not tell you definitely when it's convergent, when the series is convergent. Okay, so here's another one. So we have geometric series tests. So it's about very specific series. If you have 1 over, I want not 1 over here, something. So a times r to the power of n from 0 to infinity. So this special type of series is convergent if the absolute value of r is less than 1, and divergent if it is bigger than 1 or equal to. So let me give an example. Here, let me write here. So how about this one? So if I have 1 over square root of 2 to the power of n, when n is from 1 to infinity, is it convergent or divergent? Not 2n, it's 2 to the power of n. Let me make it here. Square root of 2 to the power of n. Is it convergent or divergent? Convergent? So what is the common ratio? Is it geometric series? Is it geometric series? Do you see the form? Do you see this series has the same form as this one? No? Yeah, I mean, the formula is not the same form, but can you turn this formula into this form? Yes, yes. So what should be A if you turn this series into this form? 1, and R could be? Uh-huh. Right. So 1, it's, you can rewrite this as this way, and then you can take out n. You can take out n outside of 1 over 2 in the exponent, and then you can rewrite this as 2 to the 1 over 2 to the power of n. Well, if you want to clean the formula, it's 1 over square root of 2 to the power of n. Okay, so r is 1 over square root of 2. So is it convergent or divergent? By the geometric, so it's a geometric series, so you can use the geometric series test. Is it convergent or divergent? Convergent, because r is less than 1. The absolute value of 1 over square root of 2 is less than 1. Square root of 2 is 1.4, or 1.414. So it's bigger than 1, so its ratio is less than 1. All right, so let's see another test, the p-test. So it's a kind of, these kind of tests will not be appear in the later semester, maybe. It will be, it's kind of a fundamental idea, fundamental theorems that we need to understand power series later. But the series test itself is kind of an exercise that our intuition is working properly here, or the practice of how you have to think about when you have this infinite situation. So p-test, or let's say p-series test, let me put this way. So what is p-series? So it's 1 over n times n to the power of p. So n from 1 to infinity. So this converges if p is less than 1. So we are assuming that p is always greater than 0. So p is less than 0, then it's actually n to the, not 1 over n something. It's actually bigger than 1. All the entries are bigger than 1. So we are assuming p is positive. And it converges when p is, bigger than 1. And diverges when p is less than or equal to 1. So here's a question. Let's look at 1 over square root of 2n, n from 1 to infinity. Is it convergent or divergent according to the p-series test? Convergent or divergent? What's the p? So first of all, is this the p-series? You can apply p-series test only when it's p-series. Is this p-series? Yes. Why? And
p equals to 1 divided by 2.
1 over 2, yes. And what about 1 over square root of 2? I can go outside, right? Well, it doesn't matter. It's not the same form here. We have a constant. But if it's convergent, it doesn't matter whether you can multiply constant on a convergent series or not. The convergence doesn't change, right? The value of limit will change, but the convergence itself, it doesn't change. So anyway, what's the p here? 1 over 2. It's less than 1. So it must be divergent, right? Yeah, well, I can check with the code if you want to, but that's, yeah, so let's think about the other tests. So I'm not addressing all the tests in the book because it's going to take a lot of time. So I'm just mentioning the important ones. So limit comparison tests. What does it say? So if you have AN, BN, whose ratio is either, so its ratio is L, so it converges. So if L is not 0 and AN converges, then, so these are two conditions that if you take the ratio, the limit exists, and at least one of them, actually, I took AN here, converges, then the limit, sorry, not limit, it's sum, n from 1 to infinity. We're talking about the series, not the sequence. So then the series Bn also converges. It's a kind of a comparison test, but you're not comparing directly. You're comparing it, comparing the limit behavior of the sequence. And you can say the same thing with the divergence. So if it diverges respectively, then it diverges respectively. So if your sequence is diverging, then there another sequence also diverges. So we'll see with this example here. Though it's sometimes very useful to think about the convergence and divergence of a complicated series. So this one, let's say we have n from infinity, n plus 1 over 2n cubed plus 2n. Have you thought about, have you seen this kind of series in high school? Does high school curriculum covers this kind of series? The convergence and divergence? Have you seen it? Have you seen this kind of series in high school? No? If you don't remember, you haven't learned about it. Yeah, it's okay. So just let's think about this series. At first, our purpose of doing this is to just check what's the convergence, whether it converges or not. So the limit comparison test clearly needs our assumption to be fixed, whether we want to find the convergence or divergence. So we need a kind of idea or intuition whether this series converges or not. So let's draw the function, or let's draw the graph of a partial sum of this series first and then see what happens. So here, I'm going to copy paste again. So the partial sum, it's complicated, but it's not that complicated. What is it? Square root, that's just n plus 1. So here, n, so n is the highest index of the partial sum. Then I am actually increasing my k. So the k is starting from 1, not 0. Although the loop, sorry, to make it clear. So loop is by the variable I, which runs from 0 to n minus 1. I have to increase by 1 to make it as k. So it's a k plus 1, because I'm trying to make it n as the same as k. So, and then divide by what? K to the power of 3, sorry, 2 times k to the power of 3 plus 2n, 2k, 2 times k, and then square root. So it's a power of 1/2. Yeah, that's a sum. And if I done this, I'm done. So let's keep the log here, log scale. Okay. So when I draw the graph, I can see clearly it's increasing. So I wouldn't see that it's increasing to infinity if I used the normal scale. Only because I used the log scale that it goes to like higher and higher. But if I just saw that this is on this scale, then it must always almost just flat. I don't know whether it's going to be flat out or not. But I know that now it's going to be diverge, right? So what I want to show is this series is divergent. Then what? I need to find a divergent sequence, an, such that if I take the ratio and the limit, that the limit is going to be something like not 0. So this is my Bn in our limit comparison test. Find an such that first an over Bn is something not some number not equals to 0, and then the sequence, a series of an diverges too. So the way you can apply the limit comparison test is make your original series or sequence clean. So the thing that makes this sequence series complicated is because we have some unnecessary terms which doesn't really matter when you talk about convergence and divergence. So think about +1 here. It doesn't really matter whether you add 1 or not when n is like million or trillion, right? It doesn't really make a big difference. So I can just get rid of 1. So let's say an has numerator n instead of n+1. And how about the denominator here? So I cannot get rid of square root, but in the square root, it doesn't really matter when your larger term is n to the cube, n cube, when you then to add 2n here, because n cube is like so large, it doesn't really affect by adding 2n to it. So it's n is million, then n cube is like so big number that even if you add million, it will not change that much in the size. So I can just get rid of 2n here. So an, it was going to be just 2n cubed, right? So this is clean. Well, I mean, I can make it 1 over square root 2 and 1 over square root of n, right? Then what? Let's take the limit of ratio. So we have an over bn. What happens? 1 over square root 2 square root n. And then in the bn, it's a kind of complicated, but let's write down everything here. N plus 1 over square root n cube plus 2n. So this whole thing is the numerator, whole thing is the denominator. So now let's use the proposition that we introduced in the beginning of our class to compute this limit. How do you compute this? Well, let's say I want to clean this up by multiplying, let's say, n on the both sides of this denominator part. So let's say I want to keep the numerator for now, and then divide by n on here and here to get the same number. So it's going to be 1 plus 1 over n. And what happens when I divide by n, the denominator? So it's going to be n squared when I make my n goes inside of the square. So it's going to be 2n plus 2 over n, right? So I'm dividing out by n squared inside of the square root. Okay. Now, can I make a statement in the proposition? Can I make use of any statement in the proposition? Well, no, because if you just take the limit of the denominator here, then this goes to 1, but this goes to infinity. So the assumption is not clear. So let's make it a little bit clean. And also, I don't want it to be 0 because that means that's not what I want. Let's say let's make it in one clean ratio. So multiplying this one and this one together, so we get square root of 2 square root of n. I have 1 plus 1 over n, and then what? Multiplying these two things, we have square root 2n plus 2 over n. Okay. Now, just forget about what I did. Just focus on this part. I want to divide by square root of n again to make it clean. So when I do that, when I have divided by square root of n, and all disappears here. So it's a 2 plus 2 over n squared. And then how about here? It's square root of 2 And this one cancels out, and 1 plus 1 over n. Right? So I didn't do anything. I didn't need to actually compute the limit. I just changed the formula of the ratio. And now I can use the proposition number 3 in the proposition here. So what's the limit of the first sequence when n goes to infinity? What's the limit? Square root of 2. And what's the limit on the denominator? Square root of 2. So what's the limit? 1. So I know that the ratio between an and bn is, limit of the ratio is 1. So the first condition is true. And the second condition, if I want to show that bn series diverges, I need to show that an series kind of diverges too. So does this diverges? We just proved it, right? By p-series test. This diverges. That is true. So what can you say? This bn series also diverges. Right? Any questions? Any questions? No? All right, so I'm going to introduce the highlight of our section here. The comparison test, whatever, limit comparison test or other tests are just to understand the power series. The definition of power series is a series of the form an times x minus c to the power of n. Here now n is starting from 0. So this is the abbreviated notation. If I write it down explicitly, that means a0 plus a1 x minus c plus a2 x minus c squared and forever. So it's an infinite series. But what is the characteristic of here? We first have x. What is x? It's an unknown variable. It's variable. I don't know the value. It's just a variable. You can plug in any number in here. And what is c? C is just a constant. It's a number. It has to be fixed. And what is an? An is also number. It's a sequence. You have a question? No? It's just a sequence. So overall, it's a number. Everything is number, but I just took a sequence as if it's a coefficient of a polynomial, but that's not a polynomial because there is no fixed degree. The degree of each term goes infinite, from 0 to infinite. Okay? So this is the power series. Whenever you have a series of this form, you call it power series. And more specifically, it's the power series with center C. So C is called the center. So why do we care about the power series? Because it allows you to compute an important function. So for example, this is one of the power series that you have to understand clearly about. So 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. This is a power series. What's the center? What's the C? 0, yes. And how does this AN look like? AN look like what? What's A0? A0 is 1. A1 is 1. A2 is 1 over 2 factorial. A3 is a 1 over 3 factorial. So AN is 1 over n factorial. Here, 0 factorial is by definition considered as 1. It makes sense. It has to be defined as 1. Okay, so NC is 0. It is power series. So my question is, it's still not a number, right? I mean, it should be a number only when you plug in some value in your variable x. Until then, it's a kind of a number, but it's not determined. The value is not determined. So what does it resembles? If you plug in a number into variable x, you get a number. So it's a function, basically. So your function could f of x could be defined using the power series, right? But when you define a function, you have to memorize, you have to know not just the formula of a function, but the domain of a function. So the function by itself, the definition of a function is information about the domain, or in easy words, it's an interval, and the formula. Formula is kind of an assignment rule. So this only gives you the formula. So now I'm curious about the domain. What value can I plug into the variable x and still get some number? So let's try to test out with a computation here. So let's see here. We have, let's define our power series. So let's say P here. So x is a variable, and n is also integer. So when you compute the power series or any series, it's inevitable that you have to use the finite sum because it's impossible to add infinitely many. But let's do it this way. I just want x. Okay, I'm going to return another real number. What I'm going to do is start from the sum, and and I'm going to define my term to be 1. The term is the sum end of each sum end of this sum, the infinite sum. The terms start from 1, and I'm going to multiply by some factor so that it moves to the next term in the series. So I'm going to do it yeah, I think that's the right syntax, right? So I'm going to loop forever. I'm not really forever, until my term is actually 0. So this is only allowed in the Python because Python can check whether it's underflow in terms of the float value. So it's not recommended for any programming language, but I just do it because it makes kind of a intuitive sense. But I'll tell you what really happens here. So, okay, so when the term is not 0, I keep adding it to the sum end here. And I'm going to update my term to the next term by multiplying. Oh, okay, so I need to set my n as 0 here, n plus 1, and n is added to 1. So n is kind of, n is an index, so my first index is 0. And then if I want to move to the next term, I have to increase my index. So this index is 1, so I need to divide out by 1 here. And then when I move to the next summand, next term, I need to multiply x and also divide it out by the index. So multiply by x and divide by the index. So index from, index was from 0. So I need to add 1 for the next index. And then I really need to update the index again to permanently change my index. So, and then I keep doing it until my summand is actually negligible. Actually, after that point, at some point, I'm adding 0, so no changes in the summand. So then I stop. So that's the end of our definition. And let's try to graph it. Okay. So in this case, I want to draw a little bit differently. So I already introduced the NumPy, so I'm going to use the package called the NumPy. And let's see. I'm going to make a list of numbers. Sorry, okay, getting bothering. Okay, so I want to make a list of values from -5 to 5 consists of 100 points. So here, did I use P? Yes, I used P. Yes. Okay, so here what it means is that I'm using a function called linspace in the NumPy package. And I call the NumPy package as NP because I abbreviate it so. And this linspace function takes 2 or 3 inputs. I used 3 because I want to make a list of 100 elements. So this 101 is actually, actually this is 101 elements, sorry. Yeah, so I want to make a list of values range from -5 to 5, including -5 and 5, including the end here. And I want the list to be equidistanced with 101 points. So if you have 101 points all the way from -1 to -5 to +5, how small is each interval here? How many intervals, how many divisions between this interval -5 to 5 if you have 101 points, including 2 boundaries here? At exactly 100 divisions, right? What did you say? Yes, it's 0.1. Yes, because the total length is 10 and I divide it by 100. So it's going to be length of 0.1 for each subinterval. So that's what I'm doing here. And that's going to be the numbers list in the list X. And in the Y, I take all the value in SQL and compute the value with the function P here. So P is basically the power function. I didn't include N, but it's there. It's kind of hidden here. So you can see a nice graph here. So whenever you have a graph, whenever you have a point, that means that it successfully computed the value. It doesn't go infinite, right? So you can see that I can put my x as small as -5 and as big as 5, but that doesn't really solve what's the domain of my power series function. So still, I have to check whether it could be below -5 or above 5 and how far I can go. So here's the definition again. So whenever you have a power series, so a positive value, R, is called the radius of convergence if the power of convergence of a power series if the power series converges when x minus c is less than r and diverges when x minus c is bigger than r. So this r is kind of a threshold where you can move your x away from the center c. So you can only get the value of power series whenever you move within the range of r from the center c. Of course, if you put the center c as a value of x, the power series always converge because except for the first term, everything goes to 0. So here is another example. So here, before I go introduce another example, I'll just give you the fact. So in this case, isn't working now. If the power series converges for all x, then we say R is infinite. It's just the symbolic notation, symbolic indication that the R, that the power series converges no matter what the value of x is. And if power series converges only at x equals to c, we write R equals to 0. So in this case, radius of convergence is infinite. That means this power series always converges no matter what value of x is. X could be, it cannot be infinitely large, but as long as you put the number here, it always converges. Let me show you another example here. So not from 1, x minus x squared over 2 plus x cubed over 3 minus x fourth over 4 plus x5 over 5, and so on. So this is also power series. Okay, so this is also power series. What is A0? Here, do you see A0 here? Do you see degree 0 term? No, there's no constant term, which means that the coefficient of a constant term, degree 0 term, is 0. How about A1? Is 1. A2, minus 1 over 2. A3, 1 over 3, and so on. And what is the center? 0, yes. So it's kind of an alternating series, but still it's not a number because it has a variable. We need to know how big the variable, how big should be in order to get a proper number. So let's try to implement this in the graph. So we just need to change a little bit here. So let's see, whenever I make a term, and so there's no zeros term, so I can just start from n equals to 1, because that's what I have. So the term basically is x to the power divided by something, but I'm not going to update the term that way because I want to reuse the term variable every time I loop here. So let's see. I'll I'm going, so depending on whether n is even or odd, I'm going to add or subtract from the sum. So if it's even, let's say this is n equals to 1, n equals to 2, 3, 4. When it's even, I have to subtract, right? So not adding. So let's subtract the term divided by n. And when it's odd, I'm going to add a term divided by n. And I increase my n and also, oh, sorry, I have to put that in here. Oh, sorry. I think I don't need to. So yes, so term here. And n equals to 1. 1 is when adding it. Yes, yes. Okay, so this is my term. And I want to keep this. I'm going to keep doing it until my term is actually 0. So let's see what happens. So I'm going to increase my number from 0 to 1 with 101 points. Therefore, each interval, sub-interval, will be 0.01. And let's draw this. Not sure whether it can draw me a graph properly. Yeah, it takes too much time because, yes, that's what I expected. So let's draw like 0.9 here. I don't need 100. I just need few of them. It still takes too much time. The reason why is because to loop this while command until the term becomes 0 when x is as close to 0.9, you have to loop quite a lot of time. So I have to take this into something like while, not while, let's make it 4, in the range of 100. So it's not going to be exactly the same value of the power series, but it's going to be a nice approximation. So yeah, so this is the graph of the function, a power series function. I only draw up to 0.9, but let's see what happens when I increase this 0.9, the right bound, to close to 1. So let's see. Yeah, let me make it more closer. So, and also I want to make it minus 0.99 and 0.9 to make it 101. And you see, so there's no issue when I get close to 1, but there's issue when I get close to -1, right? So I range my x value from as close to -1 to 1. I didn't put -1 because it's going to diverge anyway. So I'm just making it closer and closer to the -1 and 1 boundary. But let's do it more and more. You see, you can imagine when I really close to -1 and when x value is really close to -1, it's going to be decreased infinitely because look at the formula here. What happens when I plug in -1? So when x is -1, what you have is -1, -1/2, -1/3, -1/4, -1/5. And this is minus of 1/n, when n is from 1 to infinity. So we talk about p-series test. This is the p-series with a p equals to 1. So p is 1. That means it's bigger than or equal to 1. Therefore, by p-series test, it diverges. It diverges very slowly, but it still diverges. So you cannot plug in 1 in this power series. How about I mean, you cannot plug in -1, sorry. You cannot plug in -1 in this power series. How about less than -1? What happens when you plug in value less than -1? Does it converge? Let's say you plug in -2. What happens? -2 minus -2 squared, 2, -2 cubed, 3, -2 fourths, 4. Does it converge? No. Why do you think so? Why do you think it's diverge? Yeah, it's actually, I'm not sure whether it's decreasing because it's oscillating. It's actually decreasing, sorry, decreasing. Always minus. Yeah, it's decreasing. It's decreasing faster. And also, yeah, you can argue that because it's actually a good argument because that uses the comparison test, which I didn't mention in this class. But also you can use the nth term test. The first test you have to use whenever you check the convergence and divergence. And whenever you look at this is the power of 2 to the power of something and divided by something. When this goes far slower than the numerator here. The numerator is exponential. It goes infinite. Right? It doesn't go to 0. Each term, the limit of each term doesn't go to 0, so it diverges. So you cannot plug in the value less than -1 either. So there is no value you can assign to that function defined by the power series for value less than -1. So you cannot move your x away farther than -1. Now, what about the right side? So can you plug in 1 here in this power series? What happens when you plug in 1? 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. Does this series converge? Does this series converge? It's an alternating series. What does alternating series test say? It converges if the nth term converges to 0, right? Nth term is 1 over n, right? It goes to 0, so therefore it converges. So now what happens when you make x bigger than 1? What happens when you plug in 2 instead of -2? So here, so we have 2 minus 2 squared, 2 plus 2 cubed, 3, minus 2 fourths, 4, plus. Does this converge? So in this case, we don't know whether it's steadily increasing or steadily decreasing because it's oscillating. The signs is changing, but each time you add next term, the size of the term is increasing exponentially bigger. So it's like oscillating, amplitude of the oscillation is getting bigger and bigger. So it's diverging if you draw the graph. And also you know that this is diverging because of the nth term test. The nth term test doesn't say that, I mean, the limit of the nth term doesn't go to 0. So nth term test says the series must diverge. So what do you say about this now? What can you say about this graph? You cannot make a graph of this power series, away from -1 to 1. You can only plug in the value in this range. You can throw in right bound, the 1, and still get the value, some value, but you cannot include the left bound. So it's safe to just say that your interval of domain of this function is -1 to 1, not including either bound. So this series is only defined from -1 to 1, and as I said, the center is 0. What is our radius then? From 0, I can go far, at most -1 or 1. That means I can move up to distance of 1, right? So r is 1 here. I can move away from the center at most 1 unit of distance. Okay. All right, so let me finish with a small remark. Why do we doing this? Because we are going to define function using power series. So when you define a function using power series, you need to know the radius convergence because it gives you the domain of an interval of that function. So what kind of that function is? It's the most basic function you can think of and also really important, which is exponential function, cosine function, sine function, log function, and so on. So why do you need that? Because how are you ever gonna compute the exponential function or sine function without any power series, without use of power series? There's no other way than using the power series. There could be other clever way of doing it, but fundamentally they are defined by the power series. So we are laying the foundation of our mathematical calculation. You think you know the exponential function and sine function, but if you don't know how to compute it, if you go to the ancient Stone Age and you want to teach the exponential function, how you do it? You have to teach how to compute it. So that's what we are going to do in the next time. We lay down the foundation of all the theory, all the necessary terms, and next time we're going to show you, we're going to have a one toy project about making a calculator. So see you tomorrow. See you next week.